Newton's laws of motion. Newton's laws of motion dictate how forces act on a body and its motion. The first law states that in an inertial frame of reference, an object either remains at rest or continues to move at a constant velocity unless acted upon by a force. The second law states in an inertial frame of reference, the rate of change of momentum of a body is directly proportional to the force applied, and this change in momentum takes place in the direction of the applied force. The third law says all forces between two objects exist in equal magnitude and opposite direction. Now, if all of these sound a bit difficult to you, do not fret. This was in fact worded in a difficult way. I'm not sure if these are official quotes from the Principia Mathematica, but I just found them online and they seemed difficult enough for me. So let's move on to the laws themselves. The first law. I'm not going to read that again because, well, I just did. So I'm just going to tell you what it means in simple. If there's no unbalanced force, there's no acceleration. And that actually makes sense, because what the first law basically says is, unless there's a unbalanced force, an object will remain at rest or continue to move at a constant velocity. And changing one's velocity or moving from rest requires acceleration. So if there's no unbalanced force acting on the body, it will not accelerate. We see this in our everyday lives, but let's go somewhere at least we don't know. Snows. Now, ice does not actually offer any friction, which is why you can move freely. But even in that situation, you will not accelerate or move unless you push yourself forward using those poles that you carry all the time. Now, the exact opposite is true for when you've started moving on ice. Because there's no friction force to stop you, you can skate over ice very easily for a long time, and you'll have to exert a force yourself so that the friction becomes high enough for you to stop. That means your velocity remains constant unless and until you exert a force yourself to bring yourself to rest. Moving on to Newton's second law. Again, I'm not going to read all of that, I just read it a few moments ago. But let's go on to the mathematical application. What a rate of change of momentum translates to is this: final momentum minus initial momentum divided by time. And this is, of course, directly proportional to unbalanced force in a direction applied. Getting rid of the proportionality sign means applying a constant to the whole thing, and this becomes unbalanced force equals to k times rate of change in momentum. We take mass common and we get m times v minus u by t. V minus u by t becomes acceleration, and we get unbalanced force equals to k times m times a. Now here's the funny thing about an unbalanced force. We assign a value of 1 Newton to a force that is required to move a 1 kg mass with an acceleration of 1 meter per second squared, which means that k is effectively 1, which leaves us with an equation that simply says F equals to ma. Here's an application of the second law. If a 70 Newton force accelerates a 5 kg mass by a equals to 70 by 5, gives us 14 meter per second squared. An aspect of the second law that intrigues me is that it actually proves the first law. If unbalanced force is equal to 0, that means F equals to ma equals to 0. Since objects obviously have mass, acceleration must be equal to 0. And this is exactly what the first law said. Unless there's an unbalanced force exerted on the body will not accelerate or change its motion. So let's go to the third law. I'm not going to read that. I am going to read the much simpler version though. Every action has an equal and opposite reaction. We know this from a very young age, and we love this law because it's so simple. But I'm going to make this a bit difficult for you. I'm sorry, but I have to. We can actually derive the third law directly from the conservation of momentum, because if you don't have any other force acting on you, you get exactly this: momentum being conserved. m1 u1 plus m2 u2 gives us m1 v1 plus m2 v2. Now if we swap sides to take m1 in one side and m2 on the other, we get this. Take m1 common and take a minus sign, so you can change minus v1 into plus v1 and plus u1 into minus u1, and so do the same one here, but we don't need a minus sign because v1 minus u, because we already have v2 minus u2. Divide both sides with the time required to bring this change in momentum, which will of course be the same, and this gives us unbalanced force equal to unbalanced force. Notice the minus sign before the unbalanced force on one side. This tells us that for these forces to be equal, one of them must be negative while the other must be positive. This means these forces act in opposite directions as well as have the same magnitude, which is exactly what the third law says. An example of the third law, of course, is gravity, perhaps the most famous example of the third law. The gravitational pull exerted by the Earth on the Moon is the same as the gravitational force exerted by the Moon on the Earth. Now, a lot of forces exist in nature, and it's very common to confuse a few forces for third law pair forces, but there are a few rules to identify them. I'll start with the very common one. Normal reaction force and gravitational pull are not third law pair forces, even though I myself have confused them a number of times. This is because third law pair forces must act on two different objects, they must always be equal and opposite, they must have the same line of action and the same time of action. So what does all of this mean? It's easier to show you using figures. Imagine you're sitting on a surface. There's always a gravitational pull on you that's about 50 Newton downwards, and the surface is pushing you upwards with a force of 50 Newton. Now on the outside, this looks like a third law pair force system, but the thing is, both forces are acting on you. The 50 newtons of gravity are pulling you downwards, and the 50 newtons of normal reaction force are pushing you upwards. So this pair force is eliminated from the selection at the very first criteria. They do not act on two different objects, rather they act on one. But let's go deeper. Imagine you're sitting on an inclined surface with an angle of theta. Now, the normal reaction force is actually acting perpendicularly to the surface, while the gravitational force will be acting vertically downwards. This means that the normal reaction force and the gravitational force are not acting along the same line. Another thing is that because normal reaction force will now be divided into two different components, it cannot be equal to the gravitational force. So these two pair forces fail on almost all the criteria needed to become third law pair forces. I've highlighted this very clearly because, like I said, I've confused them myself several times and I've seen students do them every day, and I hope that you won't do it after watching this. There are plenty of examples for third law pair forces. You have gravitational forces, you have forces that you're exerting on your chair right now. The force you exert on your chair and the force the chair exerts on you are third law pair forces, but not gravity and the normal reaction force your chair exerts on you. Those are not third law pair forces. And that brings us to the end of our video. If you have any questions, leave it in the comment section below, as well as suggestions for the next topic. If you enjoyed the video, leave a like, subscribe to the channel, and of course, ring the bell icon.